Hi, this is the first section of a digital module that has been compiled as part of the Improve European Training Network. The module overall aims to introduce the concept of analogue modelling and to demonstrate its application in volcanology. This first section of the module is aimed at undergraduate level students, but it should also be relevant to postgraduate students if you have not had any experience in using an analogue modelling approach before. If you're interested, I'll cover more advanced material in the next section of the module. So my name is Mike James, and I'm a volcanologist in the Lancaster Environment Centre at Lancaster University in the UK. Much of the material in the module was originally compiled by my co-author Steve Lane, who is also a volcanologist at Lancaster. We've both been involved in using analogue modelling approaches over many years now. The first section of this module aims to explain what analogue modelling is and how it contributes within the broad context of investigating volcanic systems. After completing this portion of the module, you should be able to explain the main factors that make volcanic processes challenging to investigate and describe three broad styles of scientific approach that we often use. Analogue modelling is one of these styles of approach, and you should be able to explain the advantages that brings by using it. Finally, for analogue models to provide useful insight into volcanic processes, they need to be carefully designed so that they have appropriate similarities with the volcanic system. So this process is called scaling, and you should be able to explain the basic concepts of model scaling and similarity. So in this first section, we'll initially cover the physical characteristics of volcanic systems and explore why they make investigating volcanic processes so difficult. We'll then look at the different styles of scientific approaches that are used to give context for how analogue experiments can contribute to our knowledge of these systems. We'll then briefly consider two different types of analogue experiment, pseudo-analogue and full analogue, before finishing by introducing scaling and similarity. So these last two concepts are how we ensure that the information that we can get from analogue experiments is relevant to the volcanic processes or systems that we're interested in. Note that I'm not going to review the wide range of analogue models that are actually used in volcanology in this digital module. However, at the end of this introductory section, I'll provide details of some of the excellent review papers that do just this. If we consider volcanic systems, or even just the magmatic components of them, it's clear that their physical characteristics make it difficult to study the underlying processes that are involved. Temperatures and pressures can be sufficiently high to be very hazardous. The volumes, distances and masses involved can be large enough to hinder any easy measurement or to provide good spatial coverage. For most parameters, relevant values may vary over multiple orders of magnitude, which complicate things by requiring multiple different measurement methods. Magma viscosity is certainly one of these challenging parameters, with some magmas having a viscosity similar to that of warm syrup, to others that appear much more like solids. Indeed, as hot magma cools, it forms from a fluid state into a solid. When it is as a fluid, the liquid melt often contains crystals, which are solids, and bubbles of gas, so it's actually a multi-phase fluid. As it cools, the liquid melt continuously changes its properties, and the proportions and the sizes of the shapes of crystals and bubbles also continuously change. These changes can be complex and they can be non-linear, and all influence the apparent viscosity. So overall, volcanic systems represent very complex natural systems in hazardous environments over which we have no process control. Consequently, volcanic processes are generally very difficult to access and to observe or measure, which makes them challenging to investigate. We therefore need a range of approaches, and I've broadly classified them here into three different styles. One of the most familiar ways to investigate volcanic systems is through measurements, often made directly in the field. So some field measurements record the effects of processes as they occur. So for example, by measuring small movements of the ground. Seismometers do this at relatively high frequencies as they record seismic waves. Tiltmeters and methods such as GNSS can be used to record much slower motion and changes. So for example, movements of order millimeters per year as a volcano gradually deforms under gravity and tectonic forces. During eruptions, we can measure the impact that events have on the atmosphere by measuring acoustic waves generated by the volcanic activity. By using continuously running instruments and telemetering the data back to observatories for analysis, these field-based geophysical methods can give us insight into the volcanic processes as they happen. Other field-based approaches involve sampling erupted material directly in order to measure its characteristics or its composition. Measurements can be made using methods from material science or engineering style materials testing. These values can then form valuable inputs into other approaches, such as for numerical or for analog modelling. The samples also actually represent the outcome of the volcanic processes, so they can enable direct inferences on the processes to be made. However, sampling is not always straightforward due to hazards often limiting access. In some cases, limitations like this are being addressed now through using technologies such as drones, for example, to sample ash particles from within volcanic plumes. Where direct contact or access for sampling is not possible, we can also make measurements from a distance by using remote sensing methods. Remote sensing data are often collected from satellites or from airborne sensors, but they can also be from ground-based observations too. These sensors make measurements of different regions of the electromagnetic spectrum, so they can cover infrared, visible and ultraviolet wavelengths. From these data, we can infer parameters such as temperature, physical position or motion, and chemical content. Ultimately, from the parameters, we are often inferring characteristics of a process which we might actually be able to measure much more directly if we did have access on the ground. Nevertheless, remote sensing methods provide an invaluable approach that strongly complements field-based observations by allowing measurement when access is not feasible. So the next broad style of approach to consider is mathematical or numerical modelling, which we can always do safely from the office. Usually we want to understand more about a volcanic process so that we can then forecast how future events might look in order to help mitigate their impacts. So acquiring data and process understanding are actually only the very first steps. To carry out a modelling approach, we need to start with some theoretical description of the overall process that we're trying to represent. So from that, we can then estimate what appropriate physics or chemistry is involved and describe these interactions through equations. We'd normally need to quantify some constants within these equations, so for example, material properties that we can measure in the field or in the laboratory. Running the model then results in a solution to these equations, and this represents the model output. The output is only ever as good as our understanding of the underlying processes and the quality of any values that are input into the model. Thus, model output should always be considered with appropriate caution. Initial simulations should be verified to ensure that the model is working internally as expected. So, for example, to ensure that errors haven't been accidentally introduced when writing the computer code. So, wherever possible, the model results should also be validated by comparing with known observations. For example, with field-based measurements of past events. One of the advantages of numerical models is that they can also be used to explore the likely impact of different input values, in effect to consider the sensitivity of the processes to the parameters involved. However, it's key to remember that model results can only ever be as good as our understanding that went into constructing the model in the first place. The final approach to consider, and the one that we'll focus on throughout the rest of this digital module, is analogue modelling. So first, let's consider what we actually mean by an analogue. The definition here is taken from Wikipedia. An analogy is the logical thought process of transferring information or meaning from one particular subject to another. So we're using one subject to derive understanding of another. For an analogue experiment, we're using a defined experimental system to generate understanding of a volcanic system. And in volcanology, we can broadly classify analogue experimental approaches into two different types. Firstly, we can consider some experiments as pseudo-analogue experiments. This is where we might be using real volcanic materials and some volcanic conditions, for example a basaltic melt at magmatic temperatures, but over small analogue spatial scales that are feasible to achieve in a laboratory. The images here show examples. On the left, measuring crystal growth in cooling samples in a microscope with a heated stage, or on the right hand side, generating aggregates of volcanic ash particles within a laboratory fall chamber. So this makes the aggregation process much easier to study than in a real volcanic plume. So a pseudo-analogue experiment may use volcanic materials with some volcanic conditions being replicated, but with others being analogue, such as the overall smaller scale down to millimetres or a metre or so. So some such experiments can actually be carried out at much larger scales, of multiple metres or more. Necessarily, this is usually done outside, and they're often referred to as large-scale experiments. As this can be somewhat confusing because the scales involved are still generally much smaller than on a volcano. Nevertheless, the scales are much greater than those typical of pseudo-analogue experiments inside a laboratory. The example shown here of a small simulation of a volcanic plume on the left and another of a small-scale simulation of a lava flow on the right. Both these examples involve real volcanic materials, but have been carried out at overall smaller spatial scales than on the real volcanic system. These types of experiments can give valuable insight through using the natural materials, but they're difficult, they're slow and expensive to carry out. Consequently, it's not usually feasible to carry out large numbers of experiments like this in order to explore a wide range of parameter space. So the second category of analogue experiments, which can be considered as fully analogue, are those in which the materials, the conditions and the scale are all analogues of the volcanic system. So here we might be using materials such as sand or wax to represent volcanic material, for example. The examples shown in the figures are from some classic early papers, and they illustrate granular material being used to model edifice deformation in the top left, a wax-like material to model lava flows below it, and other analogue fluids to study dike intrusion and conduit processes. You can see that wax might be a useful analogue material to study lava flows with because it can be easily melted at relatively safe temperatures, and it will cool back into a solid at room temperature. So it can be used to explore how solidification processes influence the emplacement of lava flows cheaply, safely, and on easily managed spatial scales. Because experiments themselves are real systems, even if they're analogue, they can reveal otherwise unanticipated effects or interactions. Such observations can then be used to guide or to enhance numerical models or to suggest changes to field measurement campaigns. Fully analogue experiments tend to be relatively quick and cost-effective when compared to the large-scale pseudo-analogue experiments, and they can usually be run multiple times to explore parameter space. As they're carried out in controlled environments, it is also often possible to isolate specific parameters to vary. thus enabling us to explore process sensitivity to individual variables. For example, investigating how flow rate might affect the run-out distance of a wax flow. So it's important to note that analog models are almost always simplified and rather generalised representations of the natural feature or process. So you might design a model that broadly represents stratovolcanoes rather than trying to replicate one specific volcano. Model geometries are therefore usually straightforward. So, for example, using a straight vertical tube with a circular cross-section to represent a volcanic conduit, or a cone of sand to represent a volcanic edifice. So consequently, experiments are typically designed to explore first-order processes that occur widely, rather than specific processes that are found in only one specific situation. However, it's fundamental to ensure that they are designed appropriately so they can usefully represent the specific processes of interest. Now, to do that, we need to also ensure that there's some similarity between the processes that we observe in the laboratory and the processes that occur at volcanoes. Are those processes equivalent? Are we sure that the differences in parameters such as temperature or pressure are not relevant? Only when we know that there is such similarity can we get useful insight into the volcanic process from the analog experiment. So the way we try and determine similarity is through a process called scaling. And so scaling is how we try to usefully represent a system of interest, what we call the natural prototype, at a model scale that can help us observe what is actually going on. So, for example, if our natural prototype is the volcanic system, to be able to usefully explore things in the laboratory, we generally need to be able to reduce the length scale to fit inside a room, or to consider much shorter time scales so that experiments are feasible to run. We can quantify the scaling procedure through considering dimensionless ratios called scale factors, which relate properties between the model and the natural prototype. So, for example, a length scale factor would be the length ratio h star, which represents a length in a model, h subscript m, divided by the equivalent length in the natural prototype, h subscript n. So if a 10 centimetre distance across a model is intended to represent 1 kilometre in the natural prototype, a volcano, then the length scale factor would be 0.1 divided by 1000, or 10 to the minus 4. We can use these dimensionless scale factors to help design the model so that it represents a good similarity to the prototype. So the term similarity is used to describe how relevant a scaled model is to the natural prototype, and thus how much useful insight we might be able to gain into volcanic processes. If models are well scaled, they are said to have similarity, or to be similar to their prototype. And if they are similar, then we have the capability to use them to understand relevant processes. It's important to note that a model can be scaled to be useful for investigating some specific process or processes, but simultaneously it may not be well scaled for investigating others. For example, a model could be designed to explore gravitational edifice deformation very successfully, but the same model is unlikely to be of any use for investigating the attenuation of seismic waves through an edifice, because the characteristics relevant to seismic processes have not been scaled. So we can assess similarity at 3 different levels. Firstly, and most simply, we can consider geometric similarity. This basically indicates that the distances ratios between the model and the prototype are constant across the models and prototypes. In essence, does the overall shape of the model represent the overall shape of the prototype? If so, then the model be said to have geometric similarity. Now, as an experiment progresses, a model may change shape. So the next level of complexity is to determine whether we have kinematic similarity. If we have kinematic similarity, then we essentially retain geometric similarity over time. Shape changes in the model are similar to the shape changes that occur in a natural prototype. Finally, if we have geometric and kinematic similarity, then we should also consider dynamic similarity. Dynamic similarity considers the ratio of different types of forces for both the model and for the prototype. So for dynamic similarity, these ratios of forces within the model should be similar to their equivalent ratios of forces in the prototype. This is a bit of a simplification, but for example, if frictional forces are substantially larger than gravitational forces within a volcanic process, then in our analog model, frictional forces should also be much larger than gravitational forces if we are to attain dynamic similarity. We'll consider dynamic similarity in much more detail in the next section of this digital module. So let's return now to the more straightforward geometric similarity. For an easy visual example of geometric similarity, consider that we would like to make an analog model of a volcano using sand in order to study edifice deformation. Now, we're not trying to represent the full volcanic system here, but just the edifice that rises above a flatter surrounding topography. If we want our model to be geometrically similar, we need the length ratios to be constant across the model. So, for example, the ratios between the model height and the volcano height should be the same as the ratio between the model width and the volcano width. If these ratios are close, then we can say we have geometric similarity. In essence, the model is replicating the shape of the prototype, and these ratios represent the length scale factor. So we can use these scale factors in the more detailed design of the model by using them to help with the selection of analog material. So in our sand model of a volcanic edifice, how do we know if sand is a suitable analog material to use? If we were wanting to explore the edifice deformation under gravity, then we would want to ensure that the relative strength of our model, when compared with gravitational forces, will be similar to that in a volcano. So deformation is caused by stress, so if we assume that we can use stress as a proxy to estimate the required material strength, we can consider a dimensional stress ratio, here given as sigma star, which is derived from the scale factors of density, rho star, gravity, g star, and length, h star. So gravity will be effectively the same in the laboratory as at the volcano, so g star will be 1. Material densities will also be reasonably similar, so rho star can also be approximated to 1. And this leaves stress to scale by the same factor as distances, the length scale factor. So the strength of our analog material should also be scaled to the strength of a volcanic edifice by the same length scale factor. Thus, if our length scale factor is 10 to the minus 4, then our analog material should be about 10,000 times weaker than a volcanic edifice. Actually, one of the challenges here is to try and estimate what the strength of a volcanic edifice is. This can be approached by using laboratory testing of rock samples and by collecting field data on how fractured edifices are. So the results can represent a range over several orders of magnitude. It can be shown then that sand or mixtures of sand and flour can be used as suitable analog materials for this type of experiment. Now, this is a bit of a simplification because for granular materials we actually need to be considering cohesion and angle of internal friction, but thinking of things just in terms of strength gives a useful initial start. So overall, scaling of an analogue model is essential in order to derive relevant understanding from an analogue experiment, and this includes the appropriate selection of analogue materials. So analogue modelling is the third broad style of approach that we use to investigate volcanic processes. Of course, the strongest approach is actually to combine as many different independent methods as possible. Field measurements provide raw data about what is observable in the field, but they cannot usually access the subsurface processes directly. We can use engineering or materials science methods to help characterise the properties of volcanic materials sampled from the field. And our understanding of these properties can then be used to inform modelling, whether theoretical, numerical or analogue. Using computer modelling approaches can allow detailed exploration of parameter space, which can be useful when parameter values are actually poorly known. Analogue models can be useful, but they need to be very carefully scaled. Nevertheless, they can allow us to assess whether we have incorporated all the appropriate physics and chemistry within a theoretical or a numerical model. For the most robust conclusions, these independent approaches should all provide similar results. Results from different methods may not be identical due to the different measurements used, but they should provide support and consilience. They should be explainable with a consistent story. So analogue modelling can be a valuable component to this process through being a strongly independent approach that nevertheless draws on real material interactions. So in summary, the use of analogue modelling approaches in volcanology enables us to make measurements or direct observations of processes that we cannot easily observe in a volcano. We can do this in controlled laboratory environments where we may be able to adjust individual variables and explore their effects directly. Analogue models are usually generalizations of scenarios. So for example, we would try and represent a stratovolcano rather than a specific edifice. And this means that the results should be widely applicable and provide generalized insight, rather than being restricted to one particular case study location. To ensure that the modelling results are relevant to volcanic processes, models do have to be designed to provide similarity, and this is called the scaling process. The outcomes from a well-scaled analogue model can offer strong insight that naturally complements other investigative approaches such as field measurements and computer modelling. So for wider reading on this topic, I can strongly recommend these review papers here. Galland et al., Pop et al., and Roche and Carrazzo provide excellent overviews of the diverse contributions that have been made by analogue modelling approaches to understanding volcanic systems. The Roche and Carrazzo and Merle papers go into detail on some of the critical scaling issues. If you're interested in exploring an analogue modelling approach to strombolian eruptions, then see the next section of this digital module where we go into more detail for a particular case study. I'll leave you with 2 other slides of references that have been used in the compilation of this section of the digital module. Thank you.